So in this video, we are going to learn scientific notation. So scientific notation is something that I see a lot of students have issue with in Gen Chem and other science classes when they're first getting into it, because at first it doesn't quite seem intuitive. But I hope with this video, you'll be able to see why it works, and it'll become a lot easier by the end of the video. So what is scientific notation? Scientific notation is just taking hard to write numbers, hard to work with numbers, and converting those numbers into easy numbers to work with. You're just taking what was a hard number, putting it in a form that's a little bit easy to look at and to work with. So what do I mean by that? Take as an example that you're going 10 miles per hour for 10 hours. If you want to compute how many miles you went, you just do 10 times 10 and get 100. But let's say you went 1 million miles per hour for 10,000 hours. How many miles did you go? Well, not only did this and this take super long to write, and it becomes even longer the more numbers you have, it's also a little bit difficult to compute. So 1 million times 10,000 should be 10 billion. But especially once you start having numbers like maybe 3,200 or 3,000 or 37,500, I don't know, whatever, then just being able to compute this real quick becomes way more difficult. So that's the second thing that scientific notation gives us a hand with. So to use scientific notation, all you're going to do is you're going to take your big number or your small number. We'll start with big numbers. So let's say 100,000, and you're going to find the decimal point. You're going to move that decimal point over until your leading number is reached, where that leading number is 1 through 10. So in this case, it's 1. And then however many times you had to move that decimal, 1, 2, 3, 4, 5 times, you're going to use that leading number and multiply it by 10 to the power of the number of moves. So since you moved it 5 times, you have to do 1 times 10 to the power of 5. So why does this make sense? Let's see why you're allowed to do this. Let's take, for an example, the number 2000. That's another way we could write 2000. 2000 is the same thing as 200 times 10, because all we can do is divide by 10 times 10, right? If we're dividing by 10 and multiplying by 10, they cancel out, so we're not changing it at all. 2000 divided by 10 is 200, and this 10 will stick around. So now let's take this number. This is 2000. And how could we rewrite this 200 here? Well, again, we could do 200 over 10 times 10, and that'll just be 20 times 10. And then to make it equal 2000, we need to not forget about this times 10. So we'll times 10 again. Now, finally, we can do the same process for this 20, where we do 20 over 10 times 10, and that'll just be 2 times 10. And then we'll take these two numbers, times 10 times 10, just like so. Now, if you notice, now you have your original number, your original leading number, and 3 tens, 10 times 10 times 10. You should be able to realize that's just 10 to the third, 10 to the third, and then that 2 is going to be out in front, 2 times 10 to the third. And if you look over here, that would be the same as just doing 1, 2, 3, 2 times 10 to the third. And it's simple. It's as simple as every time you're moving this decimal one time, you're scaling down by a factor of 10. So if you scale down by a factor of 10, the only way that you can maintain this as the same number is by also multiplying by 10 at the same time. So if you move the decimal, you divide it by 10. You want to keep that number as 2000, you're going to have to multiply by 10. So 2000 is the same as moving the decimal once, 200, times 10. And that's the same as moving the decimal twice, 20, times 10 times 10, which is the same as moving it 3 times, 2, times 10 times 10 times 10. So now that we see how it works when you're going from large numbers to easy numbers, what about if you have a real small number and you want to make that easy? How do you do that? Well, let's take the reciprocal of what we were just working with. Let's take 0.0005, which is equal to 1 over 2000. So if we have 1 over 2000, we can write that denominator just as we did before. Because remember, we know that 2000 is the same as 2 times 10 to the third. So now we have 1 over 2 times 10 to the third, because we just proved that, right? So if we have 1 over 2 times 10 to the third, what's another way we could write that? Well, we could write 1/2 times 10 to the third. 1 over 10 to the third. I apologize. Now let's think about how we could rewrite this number so that maybe we could do something combining these two. 1/2, 1/2 is equal to 5/10. 1 divided by 2 and 5 divided by 10 are both the same number. So instead of saying 1/2, let's plug in 5/10. So now we'll have 5 over 10 times 1 over 10 to the third. You should be able to see that that's just going to be equal to top times top, 5 times 1, bottom times bottom, 10 times 10 to the third, which will be 5 over 10 to the third, or 10 to the fourth, sorry. Now you should notice if you have an exponent in the denominator, 1 over 10 to the x, that's the same thing as saying 10 to the negative x. 10 to the negative x, 1 over 10 to the x are the same thing. So since you have 5 over 10 to the fourth, that's the same thing as saying 5 times 10 to the negative fourth. And maybe that last step didn't make a ton of sense. So let's work it out a tiny bit more. You had 5 over 10 to the fourth, and that can be rewritten as 5 times 1 over 10 to the fourth. And now it should be a little bit more obvious that 1 over 10 to the fourth is the same thing as 10 to the negative fourth. So this can just be written as 5 times 10 to the negative fourth. So what's the general rule here? Well, let's take this number right here. All we had to do was move 1, 2, 3, 4 times to the right this time. And instead of adding a 1 to the 10 to the number, we just subtract 1. So we went -1, -2, -3, -4. And this is our leading number. So we got 5 times 10 to the negative fourth. And just to make sure that this all makes sense, if we had, for example, the number 1, so 1.0, let's say, we could move this decimal once, where we move it back a tens place. And that's the same as scaling up by a factor of 10, because we go from 1 to 10. So if we scale up by a factor of 10, the only way to maintain this number as being the same as it was before is if we add a dividing by 10. So we're multiplying by 10 and dividing by 10 in the same step. So every time you move the decimal point here to the right, you're really multiplying by 10. So in order to keep it the same number, you have to also divide by 10. So given that we did this a total of 4 times, we really multiplied by 10 4 times. So to maintain it the same, we also need to divide by 10 4 times, which is the same as 10 to the negative fourth. And that's why that makes sense. So one thing that's important before we move on is that in scientific notation, you are going to want to always have the leading number be between 1 and 10. So you're never going to see something like 33.7 times 10 to the second. Instead, you'd see 3.37 times 10 to the third. Technically, these two are the same things. As we've seen, this would just correspond up here. This would correspond to 3,370, as would this, 3,370. And up here, we can see we moved the decimal 1 2 times, and we got 33.7 times 10 to the second. And down here, we moved it 3 times, and we got 3.37 times 10 to the third. So technically, they're the same thing, but it becomes a lot easier if everybody's using the same thing, the same convention. So everybody goes ahead and uses this one. This is the correct one in scientific notation. So not only does scientific notation make it easier to write numbers, because you don't have to mess around with all those zeros, it also makes it easier to multiply and divide numbers. And let's explain why. So if we remember our exponents, what are the rules of exponents? If I had a number 10 to the a, and I multiplied that by 10 to the b, that is the same thing as doing 10 to the a plus b. And let's think about why. Let's say this a up here is a 2, so 10 squared, and this b right here is a 3, so 10 cubed, and we're multiplying those. What's this really saying? Well, it'll be 10 times 10 for this, so that's what 10 squared is, then multiplied by 10 times 10 times 10 over here. Well, let's count them up. 1, 2, 3, 4, 5. So 10 times 10 times 10 times 10 times 10 is just 10 to the fifth. And as we've seen, 2 plus 3 is also 5. So 2 to the 2 plus 3 is 2 to the fifth. So that shows that if you have exponents that have this, if you have exponents with the same base, that's important. This 10 has to be the same. Then you can add them. So the 2 can be added to the 3. Because really you're just multiplying the 2 or the 10 twice, and then multiplying the 10 3 times over here. So you're just multiplying the 10 2 plus 3 times in total, which is just 2 to the fifth, 10 to the fifth. Importantly as well, and similarly, if you had 10 to the a times 10 to the negative b, that's just going to be 10 to the a minus b. And why might that be? Well, if I had 10 squared and then 10 to the negative 3, all that's saying is 10 times 10 times 1 over 10 times 1 over 10 times 1 over 10. That turns into 10 times 10 over 10 times 10 times 10. We could cancel those 10s. We'll be left with 1 over 10. And that just equals 10 to the negative 1. And as we've seen, 2 minus 3 is negative 1. An important note here, you're really still adding. You're still adding a and this exponent. It's just that this exponent is negative, so you're adding a negative. You wouldn't do a minus negative b. You're not subtracting this exponent. You're still adding this exponent. So now that we have that rule taken care of, let's think about why it might make our life easier. Let's say we want to multiply together 370,000 and 4,200,000. Say we want to multiply these two big numbers together. If we write them in scientific notation, this would become, put the decimal there, 1, 2, 3, 4, 5, 3.7 times 10 to the fifth. And this would become 1, 2, 3, 4, 5, 6. So times 4.2 times 10 to the sixth. And you'll notice we'll be able to rearrange this. We can put these together. So 10 to the fifth times 10 to the sixth there, and then put these together. So 3.7 times 4.2. These two, as we've discussed earlier, are going to combine easily by just adding these two exponents. So it'll be 10 to the 5 plus 6, which is 10 to the 11th. Now all we have to do is multiply 3.7 times 4.2. 3.7 times 4.2 is equal to 15.54. So now we can see that this equals 15.54 times 10 to the 11th. And as we discussed before, you don't want this leading number to be greater than 10. So we're just going to pop this back 1, and this will turn into 1.554 times 10 times 10 to the 11th. Notice this is 10 to the first, so this becomes 1.554 times 10 to the 12th. And that just makes it a lot easier. The same is true if we have very small numbers. So let's say we want to multiply 0.0000004 by 376,000. And feel free to pause the video and see if you can work this out using scientific notation. What we would do is 1, 2, 3, 4, 5, 6, 7. So this will be 4 times 10 to the negative 7th. And we'd multiply that by 1, 2, 3, 4, 5. So multiply that by 3.76 times 10 to the 5th. Now we can rearrange. So we'll do 4 times 3.76 times 10 to the negative 7th times 10 to the 5th. Notice this negative 7 plus 5 is going to equal negative 2. So 10 to the negative 2 will be right here. And now we'll multiply this 4 and this 3.76. So 4 times 3.76 equals 15.04. So this ends up as our answer. And again, we need to move this decimal. And moving this decimal will be multiplying by 10 to the first. So that'll be adding to that to simplify. And we'll be left with 1.504 times 10 to the negative 1. So that does make it makes it quite a bit simpler. So I hope this video was helpful in showing you why we use scientific notation, why it makes sense, and how it can make your life a lot simpler, especially given that exponentiation rule.